The mysterious zero-point energy, the quantum vacuum, has been a misrepresented subject of science fiction and pseudoscience baloney for too long. Let's talk about what vacuum energy really can and really can't do. It seems pretty crazy that space itself might contain a higher density of energy than the nucleus of the atom. This is the prediction of quantum field theory, that there exists an energy of the vacuum resulting from the non-zero zero-point energies of the quantum fields that fill our universe. For the electromagnetic field alone, this energy density has been estimated to be up to a crazily high 10 to the power of 112 ergs per centimetre cubed. On the other hand, our observations of the accelerating expansion of the universe suggest a vacuum energy density of only 10 to the power of minus 8 ergs per centimetre cubed. As we discussed in our episode on the vacuum catastrophe, this mismatch between the measured and theoretical values of vacuum energy is one of the greatest unsolved problems in physics. Despite this minor glitch, quantum field theory is arguably the most successful theory in all of physics in terms of sheer predictive power. This means we should take the idea of zero-point energy seriously and are justifiably perplexed at the mismatch between theory and measurement. But the scientific validity of zero-point energy has also encouraged some pretty terrible pseudoscience and outright quackery on the subject. From accessing this energy as a free power source, to manipulating it to generate warp fields, or pushing against the vacuum energy in propulsionless spaceship engines. Today, I want to debunk some of the nonsense surrounding the quantum vacuum. Let's start with the physics. If the vacuum has an energy density of 10 to the power of ridiculous ergs per centimetre cubed, where is it? Why can't we pull infinite free energy out of nothing? Well, the answer lies in entropy and the second law of thermodynamics. Entropy can be thought of as a measure of the specialness of the arrangement of a system of particles. Higher entropy means a more disordered arrangement. The universe tends towards disorder, and so a highly unusual arrangement will decay over time. The entropy of a closed system always increases, and that's the second law of thermodynamics right there. We harness that decay of order whenever we draw energy from a system. For example, the piston in a car engine only rises when the interior chamber becomes much hotter than the exterior. The combined volume of the inside and outside of the piston chamber is in a low entropy configuration. It's a special, unusual configuration of particles. In its return to high entropy equilibrium, energy is extracted and your car accelerates. But try to drive your car in a dense 1500 Kelvin atmosphere, and that piston has no reason to rise. It's already in equilibrium. Your car doesn't go anywhere, and then it explodes. So even if a system contains a lot of energy, that energy may be inaccessible. And this would be the case even with an extremely energetic quantum vacuum. On its own, the vacuum is the same everywhere. It's already in perfect equilibrium. Energy is extracted in the movement towards equilibrium, in the increase of entropy. No such movement is possible for the vacuum, and so the vacuum contains no useful energy. This is why so-called zero-point energy machines are baloney. They claim to access an inexhaustible source of energy, but no such source exists. In order to access vacuum energy, we'd need to introduce a disequilibrium. In fact, we'd need to reduce the vacuum energy in one region of space. The universe would then try to fill that energy whole, and we could harness that to extract energy. In fact, there's one way to do this, with the Casimir effect. If you bring a pair of conducting plates very close together, a proportion of the virtual particles will be excluded from between them. By cutting off certain frequency modes between the plates, you lower the vacuum energy in that region. The result is a pressure differential that produces a measurable force, pulling the plates together. Now we talk about that in detail here. So what about building a Casimir engine? Unfortunately, no. While that initial pull between the plates may seem like a free lunch, to extract continuous energy, you need to pull the plates apart again. This takes as much energy as you originally gained. Another popular notion is that the reduction of energy between Casimir plates can be considered negative energy, and so could be useful for all of those wonderful things that negative energy can do, like opening wormholes or creating an Alcubierre warp field. Well, if we define the average vacuum energy as 0, then the Casimir effect produces negative energy. Unfortunately, the vacuum energy between Casimir plates is very much positive in an absolute sense. The gravitational effect of energy depends on its absolute value. That means the vacuum energy between Casimir plates still produces positive spatial curvature, not the negative curvature required for warp drives. Another popular use for the quantum vacuum is as a medium to push against for propulsionless engine systems like the RF resonant cavity thruster, aka the EM drive. This notion is particularly silly. The fact is, any acceleration of a real particle involves a transfer of momentum between real particles via virtual particles. Virtual particles, and hence the quantum vacuum, mediate all forces. However, it's not possible to transfer momentum from a real particle to the vacuum without getting another real particle out the other end. That momentum must be given up by the vacuum to produce real particles again. Those particles would become the propellant, carrying momentum away. In the case of the EM drive, the proposal is that microwaves within the drive's resonant cavity push against the quantum vacuum. If particles are somehow extracting momentum from the resonant cavity, then they're giving it up again to real particles, probably photons, on the outside. This would certainly produce thrust, but no more than the rather anemic photonic thruster. So don't believe the hype. Vacuum energy is real, and it's part of the fundamental clockwork of the universe, but is probably very weak, weighing in at 10 to the power of -8 ergs per centimeter cubed. And regardless of its strength, it's not accessible to us as an energy source or as a miracle resource for fast space travel. Sorry, Internet. All that said, the quantum vacuum does have its uses. Just ask the gecko. Geckos are able to cling to almost any surface by making use of van der Waals forces, which are essentially the same thing as the Casimir force. The pads of gecko feet are covered with microscopic hairs called setae. These hairs split into millions of spatula-shaped ends that are around 0.2 micrometers in diameter. When a gecko presses its cute little feet onto any surface, a fraction of these hairs are close enough to the surface so that Casimir forces come into effect. Geckos literally manipulate quantum vacuum energy to climb walls. You know what? This suggests a good challenge question. Let's say